Gabrielle de Lannoy, talking to us about, well, irrigation modeling, soil moisture and snow data assimilation for high resolution water budget estimates. So yes, please take it away, Gabrielle.
Thanks for the introduction, Andy. So digital replicas, digital twins, they're buzzwords that typically cover data assimilation output, and especially so in Europe, where ESA, the European Space Agency, wants us to work towards digital twins of the Earth. And so in this talk, we'll discuss just three aspects or three dimensions in the design of a high resolution water budget estimate for one catchment. And those three design factors are irrigation modeling, soil moisture, and snow data assimilation. Now, there's a whole team behind this, from KU Leuven in Belgium, CNR in Italy, and NASA. So many thanks to Michael, Louise, Zdenko, Sarah, Devon, Hans, Augusto, and Christian. All right, so what is our objective? We want to get the water budget dynamics over the entire Po River Basin, and that's particularly challenging because the water budget is not only controlled by natural processes, but there is a heavy human impact here. So we need to model irrigation to get the water budget correct. We further want to assimilate high-resolution satellite data for both soil moisture and snow updating. So two storages of water, and that will affect the stream flow. On top of just modeling irrigation, we also need to withdraw that irrigation from the stream flow to get our water budget correct. So this is the outline of the Po River Basin in the top three figures there. It's covering most of North Italy and a little bit of Switzerland. There is in yellow on the left side a large agricultural plain surrounded by the Alps in the north and the Apennines in the south. So those mountains will actually feed meltwater to use for irrigation. In the middle plot, you see dots. The blue dots are where we have snow depth sites. The red crosses are where we have SWE, so snow water equivalent evaluation points in space and time. It's sparse data. And then the far right plot shows you the black dots where we have stream flow gauge data in different reaches of the Po River and its branches. And so for each dot, there's a corresponding basin. So over this area, we conduct 8 experiments, or 8 digital twins, if you like, with the NOAA NP land surface model, which dynamically simulates vegetation, and we also do river routing. All simulations are at less than 1 kilometer, so high resolution, we call that, daily about 8 years worth of output. Let's start with the open loop, so that's snow data simulation. Let's look at the cube on the left there, where you see the 8 experiments, starting with the open loop in red, where we do not simulate any irrigation, so a typical land surface model output. And from there, we can then either add irrigation or add backscatter data simulation for soil moisture updating, or add snow data simulation, or do any combination thereof. So as a result, we have 4 experiments with irrigation, so the top 4, and 4 without irrigation in red, right? And then we have an open loop, 1 open loop, and then 3 corresponding data simulation experiments. All the details on the data assimilation, you can look up like the agenda paper or my perspective paper to get ideas of what are shortcomings, what are challenges in that. So I won't go into the details there. What I do want to highlight, though, is that our experiments are offline simulations. And so we need to have a lot of several assumptions on parameters, but also on input. So its meteorological input is coming from ERA 2 or from ERA 5. We chose to use ERA 5 because with ERA 5, we got our stream flow simulations closest to the observations. So the plots here, the white symbols are observations, the blue bars are simulations. Yellow is the evapotranspiration, the lines are precipitation. But it goes to say that ERA 5 better matches, although if we compare with precipitation data, that's not for the entire basin the case. But so that's our choice. Just to keep in mind that the choice of your meteorology and your parameters actually strongly affects the results of your digital twin. So the 3 dimensions here that we will implement. So the first one is irrigation. You see the open loop in red. The blue is the open loop with the irrigation, red without irrigation. And you have, at the end of July there, this peak. So you add water, soil moisture goes up, the uncertainty actually temporarily decreases and then increases again, right? So by irrigation, we change the climatology of the soil moisture. The middle plot, there we do backscatter data assimilation, more particularly the VV from Sentinel-1 is assimilated for that same period as in the first plot. You see in red the open loop, and then in yellow the data assimilation result. If you look over a long time series, you'll see that the climatology is maintained as opposed to when you do irrigation simulation. We transform backscatter to soil moisture via the water cloud model as the observation operator. And then the far right side, that's snow depth data assimilation, where again in red is the open loop, so no satellite data. The black dots are the Sentinel-1 snow depth retrievals with their uncertainty, and you see that the data assimilation in green is then tracking the observations. We only assimilate in the accumulation phase because the snow depth retrievals are not trustworthy in the melt phase. Note that the snow depth data assimilation is unbounded. We don't make it bias-free, whereas the backscatter data assimilation is bounded. The soil moisture is bounded, and we make sure that it's bias corrected. So for irrigation, well, first, the top 4 plots give you an impression of what our input of precipitation is, the output of evapotranspiration, soil moisture, and LEI, long-term averages. Precipitation has this coarse pattern where in the valley, far less precipitation is seen than in the mountains. And the consequence of that is the irrigation plot on the bottom left, where you see where irrigation is happening, less surrounding the mountains and then more towards the east and the south. If we compare the irrigation estimates against in situ data, we typically have an overestimation. But, and that will be in the next slide, if we compare a basin average to basin reports, then we estimate far too little irrigation. So we only have 180 millimeter per year, whereas the basin reports are 500 to 600 millimeters per year. And that's because the model only simulates the amount of irrigation that we need to grow the vegetation. Whereas in reality, we lose a lot of irrigation during transportation and application. And that's, of course, going into these reports. Okay, so irrigation changes the seasonal budget of the seasonal water budget. This is that evaluation that I was referring to. In brown, you have proxies of irrigation based on satellite data, whereas in blue is our open loop, and in green is the backscatter data simulation run. And you see that our simulations are always less than those of the satellite proxy, right? You also see that we have more variation because we have no limit on our water availability in the model. And you also see that the data assimilation typically simulates less irrigation than the open loop. And that's because the data assimilation of backscatter is actually already bringing soil moisture to a wetter state and thereby preventing irrigation events. That's it for irrigation. Of course, that has an impact on soil moisture, vegetation, evapotranspiration, and the whole chain. Here I'm just evaluating soil moisture. Top row is correlation, so focusing on seasonal patterns. Bottom row is anomaly correlation, where we are focusing on short-term. Andy, are you trying to say something?
No, just 2 minutes. Yeah, 2 minutes left.
Oh, okay, that's quick. Yeah, so bottom is the short-term evaluation. So left, you see it's an evaluation against SMAP 1 kilometer data. So you see on the left just the performance of the open loop. The second column shows you the effect of the data assimilation. So top row tells us that the backscatter data assimilation actually improves the soil moisture over the open loop, but it doesn't improve the short-term variability. The third column shows you how the irrigation improves the seasonal pattern with respect to the open loop, but it doesn't improve the short-term variation because we cannot model human impact, the human choices for the irrigation. And then the last figure shows you how the data assimilation with irrigation compares to the open loop with irrigation. And those impacts are lower than the one in the second column. telling you that the data assimilation and the irrigation are trying to do something similar, right? Okay. Then we also do snow data assimilation. For the sake of time, I won't go into detail, but the bottom line is we slightly improve SWE. So remember, we assimilate snow depth, we slightly improve SWE. Both snow and soil moisture will affect then our stream flow, and that's what we see here. So in terms of springs, stream flow, I'm showing here the difference in relative mean absolute differences between observations and simulations. Of the data assimilation with snow in the open loop on the left, data assimilation of backscatter in the middle, and then the joint backscatter and snow data assimilation on the right. And what you can see is that both snow and backscatter data assimilation have a positive impact on the stream flow estimates, so they decrease the errors. And if we implement both or we activate both, we have like a complementarity going on, so they amplify each other. So it's a small error reduction, but it's significant because we are talking about large volumes of meltwater in the spring. Last result slide here is for the summer. We look at the stream flow. Now we are only focusing on those gauges where the irrigated land fraction in the basin is larger than 10%. I'm looking at two metrics here, left the correlation, right the relative mean absolute difference. You see 3 bars. One is a simulation without irrigation, the second one is with irrigation, but we do not withdraw the water from the stream flow. And then the third bar is where we actually withdraw the irrigation water from the stream flow. So if you look at the first bar, just the first group of bars in the open loop, you immediately see that withdrawing irrigation water from the simulation improves the correlation, and also the mean absolute difference is reduced. What you also see is that with snow data assimilation, we actually slightly degrade our results because we don't assimilate in the spring, and we actually overestimate our snow in the spring, which causes consequently that we have too much discharge, and that actually degrades our summer stream flow. But the take-home message really is here that withdrawing the irrigation from the simulations greatly helps the discharge. Okay, so to conclude, we made several digital replicas of the water budget dynamics by including irrigation modeling and Sentinel-1 data simulation. I hope you understood that designer choices are important here. The advances in land surface modeling, meaning here irrigation, they help to improve the seasonal pattern, but we cannot mimic human choices, such as when is irrigation happening. So that's where we need to improve our observational capacity in data simulation systems. Accounting for irrigation improves our summer stream flow, and irrigation modeling and soil moisture data assimilation, they actually do something similar, so they go and interact with each other. And then both soil moisture and snow data assimilation together, they improve our spring stream flow. Now, there's lots more that I can tell you about it. The paper is in draft and it's open access. If you like to find it, the reference is down here below. Thank you.